In 1960, Freeman Dyson outlined a thought experiment. If energy demand grew steadily at just 1% per year, humanity would exhaust the power of Earth and eventually need the full output of the Sun within about 3,000 years. It was never meant as a blueprint, but as a way to show the implications of sustained compound growth. Today, recent data makes that exercise seem less abstract. In 2024, the IEA reported global energy demand rising 2.2%, with electricity use alone increasing by 4.3%. That scale of growth keeps Dyson's warning relevant. Could something like a Dyson Sphere, or more realistically, a Dyson swarm, move from speculation toward engineering? In this video, we'll examine the advances of 2025, energy trends, astronomical searches, material breakthroughs, alternative designs, and the role of AI. To see how far this idea has come, we need to begin where it all started, with Dyson's original vision. From Dyson's vision to today. When Dyson first published his idea in 1960, he was not writing a work of fantasy, but laying out a logical consequence of exponential growth in energy use. His short paper explored what might happen when a civilization's demand outstrips what a single planet can provide. Dyson suggested the most direct solution would be gathering nearly all of a star's output, not for spectacle, but because the mathematics pointed to such a necessity in the far future. Just a few pages long, the paper pushed an idea from the margins of science fiction into serious astrophysical thought. Yet almost from the beginning, the concept was misunderstood. Popular illustrations showed a gigantic rigid sphere wrapped around the Sun, as though an immense hollow shell could orbit in place. Dyson, however, never advocated such a structure. What he envisioned was a loose swarm of orbital collectors, habitats, and satellites spread through space. A continuous shell would not just be impractical, it would be unstable and tear itself apart under its own stress. Later discussions by physicists confirmed this. Mechanical analyses show that a rigid spherical shell would collapse or buckle under gravitational and structural stresses. Even though Dyson himself clarified this point, the imagery of an all-encompassing ball persisted because it offered a bold, easy visual. In contrast, the swarm he proposed, each unit occupying its own path, was less dramatic to draw but far more realistic. The swarm idea carried a key advantage: stability through independence. Individual collectors orbit according to Newtonian mechanics, so the failure of one does not compromise the larger system. No perfect construction moment is needed. New satellites could be added incrementally, each one adding to the total solar output gathered. That pragmatic detail is why the idea continued to appeal to engineers and scientists long after its introduction. To help anchor the distinction, Dyson himself pointed out that while a solid sphere seemed ruled out by physics, swarms and rings could be imagined without violating those constraints. As a useful intuition check, the so-called shell theorem shows that the net gravity inside a perfect hollow sphere is neutral. But a real rigid shell would not stay neutral. Tiny deviations would magnify into collapse. For now, it is enough to note that this is why swarms dominate today's discussion. We will return to the deeper physics later. At the time Dyson wrote, the context mattered. The early 1960s were a period of profound optimism about the future of space. The first rockets had just reached orbit, nuclear technologies promised electricity beyond limits, and many believed permanent colonies outside Earth were just around the corner. Within that climate, speaking about planetary resources hitting a ceiling found ready ears. Growth seemed boundless, and so language about growing beyond planets resonated strongly. To some, the picture of engineers filling orbital space with constructed habitats sounded like natural progress, a milestone waiting to happen once current frontiers were surpassed. Of course, the era's technological base was far from ready for anything like Dyson's suggestion. Computers were enormous mainframes with limited capability. Materials science could not yet produce structures with the strength to weight needed for large orbital projects. Even imagining massive industry in space was speculative. Dyson himself admitted this. The paper was never a literal blueprint, but a thought exercise linking mathematics with cosmic scale. He calculated that humanity might not encounter such ceilings for several thousand years, but framing the possibility shaped how many thought about civilization's ultimate trajectory. The Dyson Sphere, as the shorthand became, served as a metaphor for imagining what came after planetary limits. One reason this metaphor held power was its connection to the so-called Kardashev scale. Introduced in the 1960s by Soviet astronomer Nikolai Kardashev, the scale classified civilizations not by culture or biology, but simply by the scale of energy they used. Type I meant planetary scale, Type II indicated stellar capture, and Type III described galactic energy. A Dyson swarm represented the natural mechanism to become Type II. This kept the idea alive not just in popular culture, but in scientific conversations about detecting alien civilizations. If any society reached the point of stellar harvesting, astronomers might find traces of the waste heat leaking out, visible as unusual infrared patterns. Over time, the misinterpretation grew alongside the accurate idea. Rigid shells appeared in films, novels, and illustrations, perpetuating the dramatic image. Yet within technical circles, the corrected vision dominated. Independent satellites, mass-produced habitats, or solar collectors slowly accumulating capacity. The biggest conceptual leap was not the machinery, but the recognition that such growth could unfold incrementally. Instead of one impossible gesture of construction, the swarm could grow as needed, bridging the gap between abstract exponential growth curves and plausible next steps. That underlying logic looks different but more familiar today. In Dyson's era, global energy consumption was growing but still tiny compared to Earth's resources. Now, by the mid-2020s, demand has scaled into the tens of thousands of terawatt-hours each year. Computing forms a vast new layer of infrastructure, with machine learning training runs consuming electricity at national scales. Electric vehicles transfer mobility demand directly onto the grid. Despite high efficiency and renewable energy technologies, total demand keeps rising. Dyson's base argument, that growth continues even as efficiencies improve, still holds true and gives weight to his original reasoning. Technological advances also update the conversation. Automation and robotics offer industrial control systems orders of magnitude more sophisticated than anything in the 1960s. Materials like graphene, carbon nanotubes, and advanced composites can be created, at least in small quantities, representing progress toward the strengths that large orbital structures might require. Demonstrations of successful orbital platforms, from modular stations to light sail concepts, also show pathways Dyson himself could never have assumed were realistic so soon. While civilization remains an immense distance from building stellar swarms, the basic toolkit looks more compatible than when the idea was first proposed. But distance matters. Humanity has not yet placed permanent settlements beyond Earth orbit, let alone built industry that could maintain and expand itself in space. No one has proposed disassembling planets to use as construction feedstock. Our energy demands, while climbing, remain minuscule compared to the sun's output. The Dyson swarm remains mostly within the realm of speculation. Still, the persistence of the concept in scientific language highlights its role as a framework for understanding possible futures. Astronomers actively search for infrared signatures that might indicate alien megastructures, a testament to its credibility. Even in scientific journals, the Dyson swarm is treated not as myth, but as a clear hypothesis motivated by mathematics. The longevity of Dyson's idea probably lies in its stark simplicity. It is not rooted in arbitrary optimism like dreams of personal flying cars. Instead, it emerges straight from the problem of sustaining growth inside natural limits. Either civilizations find a way off the plateau, or growth slows and levels off. That binary choice maps clearly to either tapping stellar energy or confronting stagnation. The fact that dozens of mid-century technological projections have fallen away, while this one remains discussed both academically and popularly, speaks to its grounding in physical limits rather than passing optimism. All of which brings the question closer to the present. Are conditions developing today that echo Dyson's argument sooner than expected? The rise of computation, AI, automation, and high-demand infrastructures suggests energy growth curves are again steepening. The mathematics that once seemed distant might now feel more relevant. Whether that means humanity will ever begin such a project is another matter, but the convergence of technological capacity, demand growth, and awareness of planetary ceilings keeps the conversation alive. The enduring appeal of Dyson's vision comes from this tension. It represents not a fanciful dream, but a serious framing of sustainability and ambition at a cosmic scale. For more than 60 years, it has highlighted the mismatch between exponential demand and planetary limits, forcing us to imagine solutions so large they stretch credibility. Whether humanity pursues them or not, the idea stands as a benchmark for how far growth could one day drive us. But the reason it still resonates today is not only historical or philosophical. It is also because current energy demands are rising fast enough to keep that math in view. And so the next challenge is clear. Understanding why our energy needs in 2025 are large enough that even century-old thought experiments like Dyson's remain in serious discussion. The energy problem in 2025. The scale of global consumption in 2025 reveals a landscape where electricity has become the central fuel of modern civilization. According to the IEA, worldwide energy demand rose 2.2% in 2024 to nearly 650 exajoules, while electricity demand jumped 4.3% in the same year. These figures are not abstract. They show a system under sustained pressure. Electricity is no longer a supporting utility. It is the platform upon which data, transport, logistics, and communications all depend. Growth of even a few percentage points translates into enormous new loads on grids that were never designed for such compounding demands. That is why conversations about unconventional energy futures resurface, because the pace at which consumption grows continually tests the limits of conventional solutions. One of the most prominent drivers reshaping that trajectory is artificial intelligence. What began as a tool confined to research labs has scaled into a global infrastructure. Training large models demands computational capacity measured not in kilowatts but in megawatts, consumed over weeks of nearly continuous operation. A single state-of-the-art training run can draw as much electricity as tens of thousands of households. And the story does not end once training stops. Deployed models reside inside vast data centers that operate around the clock, responding to billions of queries, generating media, parsing logistics flows, and supporting global communication pipelines. The IEA and EMBER both flag these facilities, data centers, cloud services, and especially AI workloads, as among the central contributors to electricity demand growth in 2024. That assessment turns digitalization from an abstract trend into a quantifiable strain on real infrastructure. The rise of mass electrification in transport adds another layer. Over the past decade, electric cars shifted from experimental prototypes into production vehicles sold at scale. In many regions, automakers no longer hedge their bets with dual strategies. They commit entire fleets to electric drivetrains. Behind every one of those vehicles lies an infrastructure of charging stations, distribution upgrades, and energy reserves. Buses, trucks, and last-mile fleets now draw from the same grids that power homes and factories. The transition from liquid fuels to electrons effectively migrates a massive load into the electrical sector. Even partial penetration in aviation or shipping would amplify the trend further. Instead of gasoline demand falling away quietly, the energy burden reappears on wires and substations with new urgency. Efficiency helps, but it cannot invert the outcome. Solar modules harvest higher percentages of the photons that strike them. Appliances shave wattage while delivering more features. Batteries survive more cycles than before. Yet these improvements often accelerate adoption rather than suppress it. A cheaper kilowatt-hour makes more activities viable, more facilities electrified, more computation attempted. Economists long ago described this feedback as the rebound effect. Efficiency lowers cost per unit, demand climbs in response, and total consumption continues to grow. That effect plays out daily in statistics. Even as efficiency metrics improve, absolute energy use surges year after year. It is a cycle familiar enough that Dyson himself would have recognized the shape, had these modern industries been visible to him. The mathematics he outlined, steady growth compounded over time, did not assume new sectors bursting into existence. Yet that is what defines digital infrastructure and electrified mobility. They are accelerants layered atop the general trend. Instead of smooth and predictable curves, growth now arrives in waves, each tied to a cluster of emerging technologies. Artificial intelligence has become one such wave, forcing data centers to build faster than utilities can promise long-term supply. Transport electrification is another, embedding new load into systems that thought they were merely expanding for normal industrial growth. From the perspective of planners, this results in unexpected slope changes. Forecasts are exceeded in half the time initially projected. What looked like incremental expansion becomes structural transformation within a single decade. Renewables are growing rapidly, but they cannot flatten the curve alone. Global solar and wind capacity expand at record pace, yet the gains often trail just behind the surge in digital and mobility demand. Hydroelectric production holds steady, nuclear plants push for extended lifetimes, and storage projects scale up as materials permit. But each addition finds itself matched by new consumption. The result is a persistent squeeze. Grids must handle higher baselines while also retaining flexibility for peak loads during weather extremes. Transmission lines, transformers, and substations strain under expansion schedules they were never designed to meet. Technological optimism remains high, but the physical build-out has finite speed. Against that background, larger questions emerge about whether entirely new paradigms for energy capture will one day be required. This is where Dyson's framing still earns attention. It was never about predicting specific industries or technologies. It was about the logic of unbounded growth eventually requiring stellar scale capture. The raw numbers we see today, demand climbing despite efficiency, accelerants like AI and mobility reshaping the slope of the curve, illustrate why that logic remains relevant. No one claims society is close to attempting megastructures, but the thought experiment feels less detached when real economies exhibit the exact mathematical behavior Dyson analyzed. What once served as a far-off metaphor now operates as a pressure point at the edge of policy discussions. If growth outpaces all terrestrial expansion, the discussion inevitably looks upward, at least conceptually. Consider also the examples of scientific computation. Facilities dedicated to climate science, plasma dynamics, molecular modeling, or astrophysical simulations consume electricity at scales unimaginable in the mid-20th century. As computing capacity grows, the appetite of these projects scales accordingly. Running a global climate simulation with finer resolution requires entire racks of processors consuming megawatts for weeks. Genomic sequencing pipelines now rival industrial production in throughput and energy cost. Scale these endeavors further to planetary-level digital twins of economies or precise astrophysical surveys, and the power required extends toward fractions of stellar output. If humanity continues defining its progress through computation, the curve naturally bends toward Dyson's arithmetic sooner than cultural intuition expects. Against this backdrop, renewables act less like a permanent solution and more like a crucial delay. They extend the timeline by supplying large increments of clean capacity, but they do not abolish the structure of exponential growth. Even if efficiency accelerates in lockstep, appetite expands faster in new domains. Fusion experiments also continue, always promising scalable baseload if engineering hurdles are solved. But until then, pressure remains on the conventional mix. Fossil fuels phase out slowly, while renewables and storage fight to keep pace with expansion. The mismatch between optimism and statistics forces reflection on growth itself. Are societies willing to moderate appetite for electricity, or will the trajectory hold steady, pushing thinking toward extraordinary measures? This does not mean orbital swarm collectors or vast solar satellites are about to appear on launch schedules. It means that the reasoning behind them is sharpened by present data. Electricity is the bottleneck across every frontier: AI, mobility, science, communication, even household life. When electricity supply is tight, everything else follows. When supply expands, new demands arrive to absorb it. That underlying dynamic is what makes Dyson's idea remain within scientific conversation, 6 decades after publication. The vision is not prophecy. It is a lens showing the consequence of trends if they remain unchecked. Right now, the trends are accelerating rather than reversing. For viewers, the takeaway is less about imminent megastructures than about the structural role of energy. Growth no longer comes from population alone, or even from classic industrial output. It now originates in computation and electrification, sectors designed to run constantly at scale. Efficiency improves, but each advance lowers barriers and unleashes greater demand. This is the self-reinforcing loop that pushes consumption higher year after year. Dyson's mathematics distilled that pattern to its essence. He did not know what industries would arise, but their effect was predictable through the compounding curve of demand. And so the conversation circles back not only to theory, but also to observation. If growth is a universal pattern, then other civilizations might encounter the same dilemma and attempt their own colossal collectors. Evidence of this would not be abstract. It would leave physical signatures in the sky. What better way to test Dyson's reasoning than to ask whether the cosmos already contains examples? That question has driven astronomers to examine anomalies with growing interest, some of which briefly appeared convincing before natural explanations emerged. The search continues, with each new instrument sharpening our ability to tell artificial from natural. The intrigue of these observations is what we turn to next. False alarms and candidate stars. Conversations about Dyson swarms quickly lead to a difficult question. Has astronomy ever revealed stars that actually look like they might host one? With billions of stars under surveillance by sky surveys, outliers inevitably appear. Each unusual dataset, odd light curves, excess emissions, unexplained fluctuations, invites speculation about artificial structures. These anomalies capture public attention because they suggest a slim chance of glimpsing engineering on a stellar scale. Yet in almost every case, further scrutiny trims the mystery down to natural explanations. The search is ongoing, but its history is a cycle of excitement, investigation, and careful correction. The most widely discussed example remains Tabby's star, also catalogued as KIC 8,462,852. Its peculiar dimming pattern startled observers when first reported. Stars normally vary in light output in predictable rhythms: pulsations, eclipses from binary partners, or periodic starspot activity. Tabby's star, however, showed erratic drops, sometimes by more than 20% with no clear cycle. The irregularity set it apart from anything previously seen. Some early commentators openly speculated about orbiting collectors intermittently obstructing the star's light, an interpretation that naturally echoed Dyson's proposal. Media seized on the possibility, launching the star into international headlines. No other observation at the time had looked so compatible with the popular imagination of megastructures. As follow-up studies multiplied, however, enthusiasm gave way to clarification. Multiband photometry revealed that the dimming was stronger at blue wavelengths than at red, pointing strongly toward particulate dust. A rigid artificial structure would block light indiscriminately, but dust grains scatter shorter wavelengths more effectively. Observations also captured longer-term fading consistent with clouds drifting across our line of sight.